I would like to start by thanking the organizer, Ana Maria and Rafa, and all of the organizers for giving me this opportunity to talk today. So, usually when I start my lessons at the university where I teach bioenergetics, I like to start by saying that it's not possible to define energetics without defining first work. Today, I would like to start by saying that we cannot continue speaking about aging without defining inflammation. So, inflammation is a protective response. It is triggered to repair or to protect our tissues upon an infection or an injury. However, whereas this acute and local inflammation is protective, chronic inflammation could be deleterious and could damage our tissues, and has been associated with many pathologies, including neurodegenerative, autoimmune, cardiovascular, metabolic, bone, and muscular diseases. And what do they have in common, all these pathologies? They have three features in common. First, they involve inflammation, and they are require the participation of cells of the immune system. Second, they disrupt tissue homeostasis. And third, their incidences increase with age. So if they are considered age-associated diseases. In fact, aging itself is associated with inflammation. As we age, there is an increase of the circulating levels of certain pro-inflammatory cytokines, such as IL-6 and TNF-alpha. And this low-grade but chronic inflammation has been named inflammaging. On the other hand, anti-inflammatory mediators, such as IL-10, has been associated with families with a history of longevity, like my friend Amanda's family, whose great-grandmother passed away this summer at the age of 107. So, certain inflammatory roots and certain cytokines has been associated with aging, but still we don't know what are the contribution of the different cells of the immune system to the process of aging. Cells of the immune system have a particular set of skills, and like other cells of the body, they can migrate from one tissue to the other, searching for pathogens. Once they recognize an antigen, they transform into killing machines, and they clonally expand and start secreting high amounts of molecular mediators, including cytokines and chemokines, that could affect neighboring cells, but also cells at a distance. And all these skills are essential for host defense and for tissue homeostasis, but also can cause diseases if they are not properly controlled. In our lab, we are interested in the adaptive immune system, specifically in T lymphocytes. When a T lymphocytes recognize an antigen in the surface of an antigen-presenting cells, start to proliferate and to differentiate into the different effector subsets. During this differentiation, it acquires competence to fight different pathogens through the secretion of different mediators. But now we know that this differentiation process is not just required to fight different pathogens, but it's also essential to switch down the inflammatory response. So a successful inflammatory response is characterized by two phases. First, an initiation phase where the immune cells activated very fast and robust, and this leads to a peak of inflammatory response. And then there is a resolution phase to shoot down gradually the inflammatory response. If this resolution phase fails, we get chronic inflammation. The inflammatory response persists over the time, and we get chronic inflammation. This plasticity of the immune system to go from one pro-inflammatory to an anti-inflammatory phenotype is essential to shift from initiation to resolution. If you lose this flexibility, you will get chronic inflammation. And this is what happens as we age. One characteristic, there is a paradox because beside this chronic inflammation, as we age, we get more susceptibility to pathogens. So there is immunodeficiency. So these are the two characteristics of the on all immune system, and we are thinking what are the consequences what happens if all your immune cells age prematurely. So usually all your cells and all your tissue and all your organs age at the same rate. But what happens if your immune system ages faster than the rest of the tissues? So thinking in this idea, what we design is a mouse model. We try to get a mouse model with premature aging just in the immune system. And to achieve this goal, what we did is we focus in one of the hallmarks of aging, mitochondrial dysfunction, and we induce this hallmark in T lymphocytes. So to do this, we take advantage of one peculiarity that might make mitochondria unique. That is, it's the only organelle that has their own genome. In contrast to nuclear genome that encodes for thousands of proteins, mitochondrial DNA encodes only for 13 proteins. But these proteins are essential for the respiratory function of the mitochondria. So there is one protein, a transcription factor, that is called TFAM, that controls the levels of mitochondrial DNA. So if you deplete TFAM from a cell or a tissue, you can reduce mitochondrial DNA levels and induce a dramatic mitochondrial alteration. We did this just in T lymphocytes. So we get a mice where all the T lymphocytes are glycolytic. They need to shift their metabolism towards glycolysis in order to survive. But just one hallmark of aging in T lymphocytes induce also immunosenescence. So these T lymphocytes express immunosenescence markers, induce loss of proteostasis. There is a block in the endolysosomal system and in the function of the lysosome. And more importantly, it induces a pro-inflammatory cytokines characterized by the secretion of TNF-alpha, interferon gamma, and IL-6, the same cytokines that characterize inflammation. So we have generated a mouse model that have a stress and mitochondrial dysfunction just in the T lymphocytes, and by doing this, we get a molecular aging in the immune system. What happened with the function of the immune system? As expected, we found that this pro-inflammatory phenotype is reflected in the circulation levels of the pro-inflammatory cytokines. So if we, in the steady state, measure pro-inflammatory cytokines in this mouse, there is an increased accumulation of interferon gamma, IL-6, and TNF-alpha. And to confirm that we are facing a mouse with premature aging just in the immune system, we challenge the mice with a virus infection. We infect our mice with ectromelia virus, that is the mouse smallpox. Here you can see that the wild-type mice, all of them survive the infection. They triggers inflammation, but they are going to resolve this inflammation and survive. Our mice, in red, don't trigger inflammation, and they die all in between the 10 first days. In a similar way, if we perform the experiment with old mice. So we have a mouse model that have an immune system that looks like an AIDS immune system. The consequences of this immunodeficiency is something very obvious. These mice could be more susceptible to virus, cancer. But what are the consequences of this inflammation? This is not so clear. What are the outcomes of the inflammation? So we are working on this, and very recently, Luigi Ferrucci and Fabri published this nice review where they revise all the literature about the association between inflammation and the different pathologies. There is an association with many of them, but this is just correlative association. Just for cardiovascular diseases, there are clinical trials that have defined there is a causal relationship between inflammation and cardiovascular pathologies. So we wonder what happened with our mice, and we observed that they present cardiovascular alterations, they present signs of kidney disease, sarcopenia, anemia, physical disability, cognitive failure. So we perform behavioral tests, memory and coordination motor there. They do worst just by touching the immune system, and they have a reduced lifespan, about half. So we propose that we have a novel mouse model of age-related multimorbidity due to inflammation, and that this data suggests that inflammation is the direct cause of multimorbidity and frailty. So the next question is, how can aging-related change in the immune system affect the rest of the tissues? To answer that question, we performed a very simple experiment. We took the serum of our mice, and we incubate primary cells for 5 days with this serum. And what we get is in these primary cells acquire markers of senescence. So we propose that the mechanism is that inflammation could induce senescence, or this type of inflammation that we have in the serum of these mice. So we repeat the experiment with a cocktail of cytokines, mainly at the similar concentration that we found in the serum of the mice, with IL-6, TNF-alpha, and interferon gamma, and we found the same result. This was in vitro. What happened in vivo? To repeat this experiment in vivo, what we did, we performed bone marrow transplant assay. So in T-cell deficient mice, we transplanted our bone marrow precursor from our mice. And we wait 4 months, and in 4 months, we get signs of multimorbidity and frailty. And if we look at certain tissues, adipose tissue, kidney, we can see that in these mice appear a senescence marker. And how a movie worth 1,000 words. This is a movie. Yes. So here are 2 sisters. This one has been transplanted with bone marrow precursor from our mice, and this one has been transplanted with wild-type bone marrow precursors. So the immune system could lead to this multimorbidity and frailty phenotype. So this is our working up hypothesis. Stressed immune cells, in this case just by a mitochondrial dysfunction, but it could be another type of stress, maybe, can act as aging accelerators. So if we deplete this transcription factor, TFAM, in our T cells, we get a cytokine storm that resembles inflammation and that can induce senescence in different tissues. So could we target inflammation for preventing aging and age-associated diseases? Now we propose to use this model to try different drugs and different interventions to delay many diseases of old age. Since I have been asked not to present too much data from the lab, so I just give a flavor. We have tested different treatments, but one of them reverse the multimorbidity phenotype associated with this inflammation, and not only phenotypically and functionally, but also at transcriptomic levels. So these are the wild types. These are in red our knockout mice, and in orange are the knockout mice treated. So each time, often, we talk about aging, we talk about autophagy, nutrient sensors, metabolism, senescence, and stress. And we try to use spermidine, rapamycin, metformin, senolytic, caloric restriction to delay age-associated diseases. But all of these anti-aging drugs controls inflammation, and most of this cellular, all of this cellular process also impact inflammation. So, just to finish, our hypothesis is that inflammation is the molecular link between the aging and the chronic diseases, and that the immune system is the main controllers of this inflammation. So all of we know that our immune system is protecting us from cancer and from infections, but it also controls the rate that we age. So we want to have a long and healthy life. We have to take care of our immune system. So this is to finish. I want to thank the people in my lab. A special thanks to Gabriela Desdimico, that is the main driver of this project. Is a PhD student that has been done fantastic work, and also Elisa, Gonzalo, Juanfra, and Eva. I want also to mention Francesc Baisauli, that was the first student that works with me and that started this project. And also thanks for the funding. A special thanks for the European Research Council that allow me to make the science that I always dream, and to my institutions. So thank you very much for your attention.